All right, so let's welcome Ralph McNutt to this virtual podium here. He's going to be talking about launch vehicles, flight system considerations. And as I said earlier, this is sort of a look at how we exactly got to this sort of an architecture for the mission. Ralph?
Okay, and Michael, you're going to be doing the slides for me, is that right?
Kirby's actually driving the slides.
Kirby's got it.
I'll be helping out with the questions.
Okay, excellent. Right, so Jim gave you a very good, better than very good, an excellent description of where we are. I'm going to give you the prequel to all of this, because this certainly did not come up immediately just out of all of this study. The next one, please, Kirby. So, you know, if you go back to as far ago as 1960, the requirements for an interstellar probe have always been couched in the phrase of making a significant penetration into the local interstellar medium over a reasonable time. And that's been subject to a lot of assumptions with respect to the engineering, with respect to the science, with respect to the whims of the people sometimes that have been doing the studies. There have been a large range in both of those. One of the things that people have looked at early on were to try to see if you could get up to asymptotic escape speeds from the sun in excess of about 10 AU per year. And as you just heard, we're finding speeds with the current baseline that's been put together lower than that. So let me try to sort of walk you through some of this. Next, please, Kirby. So the solutions over the years that people have talked about have been the solar Obrich maneuver, and you just heard a lot about that. Obrich came up with this in 1929. His example was to have a delta V at the sun of 5 kilometers a second, a closest approach of about 1.5 solar radii, so from the center of the sun, so even closer than what we've been talking about here, and that would get you up to about 15 AU per year for escape. And I'll say a little bit about why those numbers just simply do not work. Of course, Obrich at the time was looking at the kinematics and wasn't worried about thermal shields. Nuclear electric propulsion has been brought up a lot. From 2003 to 2005, Project Prometheus was studied. That was a phase A study that the NASA put about $420 million into doing. The life cycle cost estimate for the spacecraft came out to about $21 billion in real year dollars, and that was not pursued. You also have to have a power supply system that's less than about 30 kilograms per kilowatt, and that's also problematic. I'll say a little bit more about that. Solar sails. Solar sails get talked about a lot. Of course, we've got solar sails that are up and flying now. There's Icaros from the Japanese Aerospace Exploration Agency, about 315 kilograms, 196 square meter sail. There's Light Sail 2 that was sponsored by the Planetary Society, about 5 kilograms and a 32 square meter sail. So solar sails work. The issue is, can you get to the kind of numbers that you would need to make sense for an interstellar probe? And I'll say a little bit more about that. Next, Kirby. So on the solar Obrich maneuver, Jim's gone through and given you a lot of the details on that. We purposely spent a lot of time on this study taking a look at exactly what Jim was talking about. I'm not going to belabor the point, but one of the things that we did do was to even go back and look at, suppose we got down to a mass as small as Pioneer 10, which was about 250 kilograms. Now, in that case, you're really not going to close the science case for this because Pioneer had a much smaller dish. You couldn't be able to do the communications that we were talking about doing. You couldn't be able to carry the kind of payload that we're talking about. But even if you did that, it turns out you wouldn't make that much difference in what we could do with the case that we've been looking at here. The scaling is very nonlinear, and it just doesn't give you that much advantage. Next, please. And so again, I mentioned about this. Basically, the spacecraft design just simply doesn't close if you were to go to a smaller spacecraft. You've also got then the issue of, well, okay, is there anything that you could do to make all of this work? And about the only lever that you're left with is to do something with the rocket engine. The problem is, as Jim was noting, by the time that you worry about the thermal shields, you've got a substantial mass that you've got to take down into the sun. And so you could say, well, okay, what else could I do about that? And of course, one of the things that one could think about doing would be to upping the specific impulse for the rocket engine, except for the fact that we're at the limits of what you can do for a solid rocket motor. You could think about getting up to, suppose you could do liquid hydrogen and liquid oxygen, but in the same mass of a rocket engine. Well, you could talk about getting up to fairly substantial speeds. You could also think about doing that with a nuclear thermal rocket. But if you take a look at those, first of all, you've got the problem that you'd have to deal with zero boil off of liquid hydrogen in deep space for 3 years. A lot of talk about that, but we're certainly not there yet with respect to the technology. And if you look at the smallest of the small nuclear rocket engines, the engine itself is approximately the same size as the kick stage, including the propellant we're talking about here. So again, the scalings just do not work. The technology is simply not there. And one simply cannot put the kind of situation together that would somehow draw on these other concepts, which aren't even technologies that yet exist in order to do this. Next one, please. Nuclear electric propulsion. Again, this was talked about under Project Prometheus. The US has only flown one space nuclear reactor. That was SNAP-10 in April of 1965. Satellite failed at 43 days. The reactor scrammed and disassembled on command, and the pieces are still up in a nuclear safe orbit. There was actually an electric rocket engine that was supposed to be powered with the reactor, and that test was sporadic at best during that time. The SNAP program in developing that reactor ran from 1956 to 73. Now your dollars, we spent about $8 billion and never got to a substantial flight reactor. There's also a major issue with respect to getting rid of waste heat, because you've got a lot of excess heat you've got to get rid of, and the only way that you can get rid of it in space is with radiator panels. This was looked at very carefully in Project Prometheus and was a huge mass driver. So for example, the reactor module came in at about 6,100 kilograms, and then the waste heat rejection segment was about another 3,000 kilograms on top of that. And this is the sort of the minimal thing that you need to be able to do something like this. So again, the technology is not there. We do not have even a clear path to the technology or a clear path to getting to the money that you would need that was identified in Prometheus that would be needed. Next, please. Okay, solar sails. All right, so I can fly a solar sail. As I mentioned, it's been done. We're doing it now. But to be able to do rapid solar system escape, you need the so-called lightness number to be greater than or equal to unity. And that is that the radiation pressure force from the sun needs to be at least balancing the gravitational force of the sun. So it turns out to do that, you've got to have a specific area per mass per unit area of less than about 1.5 grams per square meter, and for the whole assemblage. And that is hard to do. You also, in order to be able to get the speed up, you needed to actually unfurl your sail or be able to turn it to the sun, close into the sun. Maybe it's some, people have talked about 20 to 25 solar radii. So that means you need another additional heat shield if you're going to do that. And again, that brings the mass up, which implies that the shield is going to, or that the sail is going to have to be even bigger still. Right now, there's no way that we've got of being able to fly a craft that would be able to do the science closure on what has been advocated by the science team here. The solar cruiser is in development for flight, I believe, in 2025. That would be around 1 AU. It's being coordinated out of Marshall Space Flight Center. It's got a sail that's about 1,650 square meters. It's a 90 kilogram 3U space CubeSat. That comes in with a lightness number of about 0.03, which is a lot less than 1. So it's certainly going to work, but it's not going to be of the class of what you would need to be able to get significant speeds out of the solar system. Next, please. So you could think about Parker Solar Probe as sort of a prototype of something that could come close to having the capability of carrying the kinds of instruments that we're talking about here for science closure. It's also got a thermal shield that could easily take you down to 20 to 25 solar radii. So you could ask the question of, well, for 685 kilograms, how big of a sail would I need? And the answer is you'd need about a half a square kilometer. That means that if you've got spars that are hanging onto the shield, those would have to be almost 500 meters long. They would also have to carry a lot of radiation or pressure down close to the sun. And the real problem is the strength of the assemblage. And you typically would tend to get the kind of problem that you get with an umbrella in a very, very stiff breeze. That is, you wouldn't be able to stand the structural mass. So again, maybe one could get there, but we are a long, long way from doing that. Next, please. Okay, so ballistic missiles. Well, these have been around for a while. Of course, Tsiolkovsky talked about them in 1911. Goddard invented the liquid rocket back in 1926, but the real development took World War II and the V2, which was still the most, holds the record for the most number of rockets of one kind that was ever built. Next, please. And basically what happened was with the Cold War, we jumped into, along with, in the US, along with the Soviet Union, into trying to take advantage of what had been developed by the Germans on the V2 and coming up with really large rockets. The race to the moon, of course, led to the Soviet N-1 rocket that led to the Saturn V in the US. These super heavy launch vehicles were what were required to take people to the moon and back. The F1 engine that was the key to the Saturn V actually began development back in the 1950s. And in FY91 dollars actually took about 8 years and about $2 billion to development. So these things are not cheap. They take a long time. We had 13 successful flights of the Saturn V. There were 4 attempted flights of the Soviet N-1. All those ended in failure. Next, please. So that's kind of where we stood with respect to tools. And then in 2008, there was a general question of NASA science missions enabled by the Constellation launch system, particularly the Ares 5. And this led to a National Academy's report on the subject in 2008. We'd been doing work at APL on trying to look at what one could do with radioisotope electric propulsion. And so we decided to take a look on our own nickel about what one could perhaps do if one had an Ares 5. Next, please. So it turns out it looked sort of promising. So from 2009 to 2017, we looked a lot, again, unfunded, on exploring various ballistic approaches. This is all documented in various papers at the International Astronautical Congresses that ran during that time frame. And again, from 2009 up until 2017, these are all out in the open literature. Next, please. And so this particular effort that we're doing right now was funded in 2018. And we've continued to document what we've been doing at the IAC. And as a matter of fact, we're going to have a paper that's due to be delivered at Dubai next month as well. Next, please. So we cast a wide look at what we could do with various upper stages, things that were near-term historical, like the Centaur D, as well as things that are currently in production. Next. Combine those with information that we got from our colleagues at Marshall Space Flight Center on the SLS Block 2, and looked at how that you could stack these various stages together. And Rob Stoke will be talking some more about this later. Next. And then Marshall actually went and developed performance details for 18 different combinations of launch vehicles and kick stages, and we were able to use those as the basis for making the initial analyses to see what made sense. It's not that we're particularly wedded to the SLS per se, but the SLS had the data that was available, and Marshall has been incredibly helpful in helping us with seeing what one can do. Next step, please. And just to point out that if you do a plot of the injected mass versus C3 on a semi-log plot, you can actually see how that the staging helps. The various curves tend to fall off. They fall off at lower characteristic energies, fewer number of stages you have. And again, in taking a look at this, you can see that we were looking at being able to get to C3s that were up in the range of 300 to almost 450 for the kinds of masses that we were talking about. And so this gave, again, some credence to the idea that we ought to be able to do something worthwhile with a ballistic rocket, as long as we had a really big one. Next, please. And I think that's it. So thank you for your time on that. And again, these will all be posted.
All right, thank you, Ralph. We have a question in the chat from Tony Freeman. It says, for your baseline trajectory, I understand the importance of using heritage systems, which gives you a very conventional number for the spacecraft mass, 900 kilograms. Did you look at a more aggressive use of small sat avionics, small sat instruments, deployable reflector antennas, etc., to bring the mass down? If your 0.17 AU per year relationship holds up, you could get another 1.53 AU per year if you dropped the spacecraft mass to 450 kilograms.
Well, let me say a little bit about that, and then I'll call on Jim as well. So actually, when we started looking at all this, we looked at what you could do with something like New Horizons. We did not particularly address, really heroics with respect to the avionics, because of the technology horizon we assumed in the study. And Jim, you want to say some more about that?
Sure, I can do that. So the biggest issue is communications. And well, there's two really big issues. One is communications. And there's really, whenever we're trying to communicate from, multi-hundred AU, there's really only a few ways to do that really work. One is a really big dish at X-band. And another is, we did look at deployable dishes. It can reduce mass. There were concerns about the ability to deploy into the accuracy that would be required for, basically so we don't overwhelm the pointing requirements on the spacecraft. We looked at Ka band with smaller dishes. Again, there are real complexities there with pointing requirements for Ka, and the same is true for optical. So, for instance, that's an area that's really driven by, the need to have a data link, which drives up the mass, which means we have to drive up the spacecraft size to support that. The other side of that is also the two RTGs, which themselves are pretty heavy. They're on the order of 60 kilograms a piece, and frankly, they're the size of a small sat themselves. So again, there's a lot of structure that has to be had that starts to drive now, the masses that we can get down. I would say that there are some options that are talked about in the concept study report to some extent, and I do expect that if we were to do a real design at PDR time, hopefully you would see masses come down, because we would take advantage of some of the things that you're talking about. But if the purpose of this study was to show that it can be done at low risk, and I think we have that, now those are optimization trades that could be done later. If that makes sense. I see there's also a question about the RTG coming from the DOE. Yes, we have assumed the Next Generation Rtg, which is actually two of them, which is the new design that's being worked on based on the GPHS, which, for instance, was used on New Horizons.
And June Zakrajik, who's going to be talking this afternoon, will be talking about that in particular.
Yep. So I see there's a question here on an estimation of the cost it would take to build a viable solid fuel rocket. Ralph, do we have any information about that? I don't know that we've ever looked at that cost.
Well, I mean, we know for let's see, a viable solid fuel rocket. The additional mass not balanced by the thrust, making it unviable to even. I guess I'm not quite sure what the question is.
So I think about solid rocket motors, right? At this point, if we were to build try to build a higher performance solid rocket motor.
Yeah, I mean, the thing is that what's happened is that, again, if you look at the development of rocket engines, these things take tens of millions of dollars to develop in multiple years, and basically we've been building them long enough that we've pretty much squeezed every bit of performance out of these things that you possibly could. I mean, we, as Jim remembers, we looked at APL at the Star 48 GXV, which was perhaps would give one a little bit more performance for Parker Solar Probe. We ended up making a trade and going back to the Star 48 BV, which had been in service longer, but it was going to make some difference, but not that much. I mean, basically, you can push the envelope. You're not going to get much beyond a specific impulse of about 300 seconds because you're limited by the physics and the chemistry of the rocket fuel.
Yep, exactly. All right, go ahead.
I was just going to say that I think we are a little bit, oh, I'm sorry. I'm looking at the wrong time slot here. We are 1 minute over. And